Hi, Assalamualaikum and good day to all students. For this video, we are going to cover for tutorial 3 of FST209 for food engineering. And I do hope that you have done your part to answer your question in tutorial 3. Alright, so I will give the answer for each question, and any question that you highlighted will be discussed after all of these answers. Alright, so for question 1, for tutorial 3, this one relating to the heat balance, alright, energy balance. So for tutorial 3, question number 1, number 2, number 2 and number 3, this one basically is a very basic question. You just need to apply the equation of Q equals to mCp delta T. Alright, so for tutorial 3, this one we are going to use the equation of Q equals to mCp delta T for question number 1, question number 2 and question number 3. Right, and the same thing goes for question number 4 and question number 5, but of course question number 4 and question number 5 you will require more comprehensive calculation compared to question number 1, 2 and 3. Alright, so for question 1, the question asks you calculate the heat required to increase the temperature of 0.85 kilogram steak that contains 18% of protein, 14% of fat, 9% of carbohydrate and 59% of water from the temperature of 20 degrees to 90 degrees Celsius. So use the specific heat equation given, and the unit given in the tutorial is joule per kilogram degree Celsius. Alright, so specific heat equation has been given in the problem statement. Alright, for Cp, and the unit has been given as well. It is joule per kilogram degree Celsius. Alright, so the equation of Cp, you need to use the one that has been provided to you. And we have the value of 1674, Cp equals to 1674.72 times by fat fraction. Alright, so what is the value for fat fraction? The fat fraction is 14%. Okay, 14% is fat. So this one is when you divide 14%, when you divide 14 per 100, it becomes 0.14. Alright, and then we have water fraction plus 4186.8 times by water fraction. Water fraction has been given as 59%. Okay, 59% of water, H2O. So when you divide 59 divide by 100, you will get 0.59. Okay, and then plus 837.36 times by solid non-fat fraction. Solid non-fat fraction is for which part? Anything that does not equivalent to fat and it does not contain water, because water, it has its own value, it has its own specific value, and fat, it has its own specific heat value. Alright, so for solid non-fat, this one normally we will denote as SNF. Solid non-fat, this one is the one that we have from the problem statement is protein plus carbohydrate. Alright, so for protein is 18% and carbohydrate is 9%. Okay, so just use these particular values, alright, and then put into the specific heat. So this one you need to calculate what is the value for solid non-fat. Okay, and then just plug in into the equation of Cp. After you get the value of Cp, find the delta T. Delta T is in between 20 to 90 degrees. So 90 minus by 20 degrees Celsius. You will get 70 degrees Celsius. Alright, so calculate the Q, mCp delta T. M has been given as 0.85 kilograms. So times by Cp, calculate the Cp. This value for Cp is 2930.76 joule per kilogram degree Celsius. Alright, then you should be able to get as Q as 174.38 kilojoule. Okay, can you see this one, kilo? Meaning that this one is 174.38 times by 10 to the power of 3 joule. Okay, so this one I simplify the answer as kilojoule. Alright, then we move on to question number 2. For question number 2, we have question 2A and question 2B. Okay, for question 2, calculate the heat required to increase the temperature of 0.25 kg burger, so the mass is 0.25, that contain 12% protein, 13% fat, 10% carbohydrate, and 65% of water from 10 degrees Celsius to 80 degrees Celsius. Express this question in BTU. So for question A, question 2A, you need to express the Q, alright, the heat required in BTU, whereby for question 2B, it must be in joule. Okay? Alright, so for question 2A, use the following specific heat equation. Okay, after the word of B, joules, then can you see the following statement? Use the following specific heat equation. So equation number 1, so for 2A, you need to use equation number 1. Equation 1. For 2B, you need to use equation number 2. Because why? Because equation number 1, this one is meant for British unit. Whereby equation 2, this one is meant for SI unit. Alright, so that's why you need to know which equation that you want to use for which question. Okay, so for question 2A, the answer for CP is 0.746 BTU per pound degree Fahrenheit, and the answer for Q is 51.81 BTU. For question 2B, the answer for CP, this one is in SI unit. CP is 3123.35 joule per kilogram degree Celsius, whereby the Q is 54.66 kilojoule. Okay, can you see this one is kilojoule? I simplify this one, so it can be like 54.66 times by 10 to the power of 3 joule. Okay, it's the same thing. If you answer like this, is the correct answer. If you answer kilojoule, it's correct as well. Alright, then we move on to question number 3. Question number 3 is similar question pattern like question 1 and question 2. For question 3, calculate the heat required in joule. Okay, it's already given to you, the instruction in joule, to remove from 1 kg papaya juice that contain 86% of water if the temperature of juice is reduced from 70 degrees Celsius to 5 degrees Celsius. Again, this one is very straightforward. Just use the equation of Q equals to mCp delta T. Alright, so calculate, okay, where is the CP that you need to use? Okay. For calculation of CP for question 3, this one very straightforward because the papaya containing the highlighted composition is only moisture, whereby the water is 86%. Okay. 86. So because of water, can you see from the equation number 1, from question number 1, alright, the value in order for you to calculate for CP of water, you need to use the value of 4186.8 times by 0.86. Alright, so this particular value, you will get as 3600.65 joule per kilogram degree Celsius. Okay, and then plug in the value of Q equals to mCp delta T. Okay, calculate the delta T. The mass is given as 1 kg. So the answer for Q is 234.04 kilojoule. Right? Again, this one I simplify the answer. Your answer when you press your calculator, it should be around 234,042.25 joule. Okay, so that's why I simplified to become kilojoule, 234.04 kilojoule. Okay, now we move on to question number 4. Basically, for question number 4, this one, the answer will be around 10 marks when you need to calculate this one. So an autoclave contains 1000 cans of pea soup. It is being heated to an overall temperature of 100 degrees Celsius. If the cans are to be cooled to 40 degrees Celsius before leaving the autoclave, how much cooling water is required if it enters at 15 degrees Celsius and leaves at 35 degrees Celsius? Okay, the specific heat are being given in the question. Right, you have the specific heat for pea soup, for the canned metal. You need to remember that each material, they are having their own specific heat. So that's why the specific heat of pea soup and canned metal are being separated, although the pea soup is containing in the canned metal. Okay, because they are a different material. Pea soup is different from canned metal. Different material, right? The weight of each can is 60 grams and it contains 0.45 kilograms of pea soup. Assume that the heat content of autoclave walls above 40 degrees Celsius is 1.6 times by 10 to the power 4 and that there is no heat loss through the walls. Okay, so what you need to do is you need to calculate how much cooling water, the mass of water, cooling water required to cool down the process. Okay, so basically this particular question, question number 4, is almost similar like what you had in tutorial 2. Okay, so for the answer of mass of water, this one is 1534.51 kilograms. Okay, I will show you how we solve this particular problem afterwards. Okay, now we move on to question number 5. For question number 5, a liquid food product is being cooled from 80 degrees Celsius to 30 degrees Celsius in an indirect heat exchanger by using cold water as a cooling medium. If the product mass flow rate is 2000 kg per hour, determine the water flow rate. Alright, so that is your instruction there. You need to calculate the water flow rate required to accomplish product cooling if the water is allowed to increase from 5 degrees to 25 degrees in the heat exchanger. The specific heat of liquid food product and water are 3.8 kilojoule per kilogram Kelvin and 4.186 kilojoule per kilogram respectively. Okay, again, question number 5. This one is almost similar with how you want to solve the problem with question number 4. Alright, the bases are similar except that the value are different. Okay, so for question number 5, the water flow rate, we are calculating water flow rate. We are not calculating mass of water. Mass of water is in question number 4. Water flow rate is question number 5. So for water flow rate, the answer is 4538.94 kilogram per hour. Why you have per hour? Because now we are talking about the rate. When we have the rate, it must be always over time. Okay, it can be per second, per hour, per minute. As long as when we talk about rate, then it must be related with the time of the processing. Alright, so I ask you which question that you want me to explain further. So the first question that you want me to explain is for question number 2A. For question number 2A, this one is very simple actually. You just need to use the correct equation. Alright, so again, for question A, 2A, you need to use equation 1. Alright, in order for you to solve the problem for CP. So first thing first, since you can see that the value of Cp is in British unit, so what you need to do is the value of temperature in the problem statement, 10 degrees, 80 degrees Celsius, you need to convert to degree Fahrenheit by using the equation of temperature conversion given to you. Okay, it's very straightforward. So just convert first the temperature. For 10 degrees Celsius, it is equivalent to 50 degrees Fahrenheit. For 80 degrees Celsius, it is equivalent to 176 degrees Fahrenheit, right? So calculate delta T, it becomes 126 degrees Fahrenheit. Alright, so the percentage of each component has been given to you. Alright, we have 12% protein, 13% fat, 10% carbohydrate, and 65% of water. So plug in the value for fat fraction 0.13. This one coming from 13% of fat. Alright, and then 1 times by, this one is water fraction, this one is H2O, this one is fat. Okay, H2O is 0.65 because you have 65% of water. And then for solid non-fat, this one is SNF. Solid non-fat, it comes from the protein. This one is protein. And 0.1, this one is carbohydrate. Okay, this one very clear cut. So calculate your answer and remember that you need to calculate for each component first, then only you add up the value. So you should be able to get 0.746 BTU per pound degree Fahrenheit for the Cp. Use the value of Cp to calculate for Q. Again, Q equals to mCp delta T. Alright, so plug in all the values that you have calculated just now. So this one is delta T, this one is your Cp, and this one is your mass. Okay, why the mass is 0.25 times by 2.2046? This one is because you want to convert from kg to pound. Alright, so you should be able to get the value of 51.81 BTU. Okay, so that's the answer for question 2A. Very simple, nothing much for that. Now we move on for question number 4. Okay, for question number 4, first thing first, what you need to do is you need to draw the diagram. And from the diagram, you need to collect all the data given from the question, from the problem statement. Okay, so the cooling water entering into the system at 15 degrees Celsius, right? And then the cooling water exit the system at 35 degrees Celsius. Can you see the temperature is increasing? The temperature of cooling water increasing because the cooling water has absorbed the heat from the system. Okay, the system is at 100 degrees Celsius. So this particular heat from the system is being absorbed by the cooling water. So the temperature of cooling water increased from 15 degrees Celsius to 35 degrees Celsius. Alright, inside the autoclave, we have 1000 cans. 1000 cans of pea soup. Okay, 1000 cans of pea soup inside the autoclave. And since the temperature is 100 degrees Celsius, so we have this Q walls equals to 1.6 times by 10 to the power 4 kilojoule. Okay, this particular Q wall is only on this part for Q wall because this part is more than 40 degrees Celsius. Remember, the value for Q wall above 40 degrees Celsius. Okay, but the product, when it goes out, is already achieving 40 degrees Celsius, meaning that from this part onwards, we don't have Q wall. Okay, Q wall only exists when the temperature is above than 40 degrees Celsius. Clear on that? Alright, so now we collect all the data from the problem statement. So from problem statement, Cp of pea soup is 4.1 kilojoule per kilogram degree Celsius. Cp for can metal is 0.5 kilojoule per kilogram degree Celsius. Then we have weight of can. Okay, each can, it has the weight of 60 gram. Okay, you need to convert to kilograms from gram because this one is to ease your calculation. Can you see the unit here using is kilogram? Alright, weight of pea soup in the can, each can it contains 0.45 kilograms. Okay, so how are we going to calculate for the heat entering? Okay, you have been given with Cp, you have been given with mass. Again, for question number 4, you need to use equation of Q equals to mCp delta T. Okay, M has been given and you need to calculate for each material. Okay, we have can for material number 1. We have material of pea soup, number 2. Number 3, we have autoclave walls because the temperature of product, this one is greater than 40 degrees Celsius. Okay. Then you have the Q for water. Q for water, we are calculating for the mass of water. So we do not know what is the mass of water. This one is the unknown. Alright. And you have been given the Cp for water. So just plug in the value for Cp of water and then the delta T. Okay, delta T starts from 15 degrees Celsius to 35 degrees Celsius. The entering temperature is 15. The exiting temperature is, oh sorry, this one should be, okay, so 40 degrees Celsius, this one is the exiting temperature for the product material. Alright, our basis now, your basis of temperature is the exiting product temperature. Okay, basis of the final temperature. Basis for final temperature. Okay, so this one is 15 minus by 40 degrees Celsius. So you will get negative 104.67 MW because MW is unknown, kilojoule. And can you see at the end of each material, because this one is Q. Okay, this one is Q. Q is, the unit for Q is joule. Right, so this one is kilojoule. Where does this kilojoule coming from? From the Cp. The value given in Cp is kilojoule. So that's why your final unit for each Q of the material is kilojoule. Okay, and then we move on to heat leaving. Again, you need to calculate the same thing. Heat in cans. How much is heat in cans? Times by 0.5 times by 40 times by 40. Okay, 40, this one is a final temperature. And remember, this one is our basis final temperature. So that's why it is 40 divided by 40. 40 subtract by 40 minus by 40. For pea soup, the same thing goes. All of these values are the same. Okay? You need to plug in again to this particular each material. Together with the Cp, together with the mass. But then what differentiate between heat entering and heat leaving is the temperature difference. Okay, because for product outlet, it exits at 40 degrees Celsius. Okay, so our basis is final temperature. So that's why you get for the heat in cans is 40 minus by 40. The pea soup is 40 minus by 40. For heat in autoclave walls, you don't have any value. It is 0 kilojoule because this particular part is already 40 degrees Celsius. Q wall only exists for the temperature more than 40 degrees Celsius. Okay, so heat in water, again, mass of water, we do not know what is the mass of water, times by the Cp of water times by delta T. Okay, this one is the exit temperature of water. Right, can you see here 35 minus by 40 is coming from here, 35. Okay, so you will get for heat in water is negative 20.93 MW kilojoule. MW still is the unknown. So for heat entering, Q enters and Q leaving, we have the unknown of MW, the same unknown. So now by calculating, you need to calculate what is the total for the heat entering. Okay, calculate the total of heat entering, but then of course since you have the unknown of MW, you cannot add up this value to this value. Okay, because this one is a one single value on its own. Okay, the same thing goes for total heat leaving. This one is on its own. You cannot add to the other values because this particular value, they have the unknowns that attach to them. Alright, so add up the total of heat entering and the total heat leaving. So by using the Newton's law, whereby the thermodynamics law, whereby the heat entering is equivalent to the heat leaving. So Q enter, this one Q in equals to Q out. Alright, so this one is actually, this value is 128,500 minus by 104.67 MW equals to negative 20.93 MW. So the value for MW, the mass of water is 1534.51 kilogram, because the one that we are looking for is MW, mass of water. Alright, so that is the tutorial 3 that you asked for further explanation for question number 4. For question number 5, the working calculation is almost similar, except that the question asks you to calculate for the water flow rate, whereby for question number 4, you need to calculate for the mass of water. Okay, so the working calculation for question number 4 and question number 5 is almost similar, and basically this particular question for question number 5, question number 4, it will carry you 10 marks. Okay, so please try to work on your own for question of tutorial 3, and we are going to discuss on the next tutorial question. Okay, thank you.